Okay, we're going to continue with exercise 1F, and the second part of this is to do with something called roots of unity. Now, roots of unity makes you think of 1. So roots of unity are equations that are in the form z to the power of n equals 1. So what are the roots of 1? Now, it's really interesting. We've actually already worked out some of we worked out the cube roots of 1 earlier on, and obviously one of them was just 1. I think the second one that we had from earlier was a half plus root 3 over 2i. So that's minus half plus root 3 over 2i. And you can see which one this is corresponding to because it is minus a half plus root 3 over 2i. And you can also see by the geometry of this situation that the third one is going to be minus a half minus root 3 over 2i. And it's interesting to note here that z2 is actually the complex conjugate of z3 and vice versa, okay? That they have the same real part, but the imaginary part has just gone from plus to minus, okay? So I've plotted these on the diagram, and earlier on I think I did this little bit of I drew them together here, and I said that they make this lovely equilateral triangle. Okay, we're now going to do the same thing with z to the power of 4 equals 1, but I'm not going to go through quite as long a process as I did, because I think there's going to be a quicker way of solving this. Now, if z to the power of 4 equals 1, I'm obviously going to be able to work out what some of these roots are. I'm going to square root it to begin with. So z squared is either going to be equal to plus or minus 1. Well, if z squared is equal to 1, then z would be equal to plus or minus 1. And if z squared was equal to minus 1, then z would be equal to the positive and negative square root of minus 1, which is plus and minus I. So we have that z1 is equal to 1, we have that z2 is equal to I, z3 is equal to minus 1, and z4, the solutions to this, are also equal to minus I. Notice how I've got 1 and minus 1, and I have I and minus I from here. Now I'm going to plot these onto an Argand diagram. When I plot these on an Argand diagram, I have my first root, which is just z1 at 1. Then I'm going to have my second one, which is z2 at I. My third one is z3, which is at minus 1. And my fourth one is z4, which is at minus I. And we can see that all of these angles here are going to be pi over 2. Let's just quickly add that in as well. So pi over 2. Think about where the pi over 2 comes from. It comes from the fact when we plus or minus the 2 pi over n, it's plus or minus pi over 2. And in this one, where it's plus or minus 2 pi over n, in this case it's 3, you're adding and subtracting the 2 pi over 3, which is why you've got that angle there. So these are all pi over 2. And if I do what I did with the previous diagram, and I connect these together, I'm hoping you can see what shape we've got here. A square. A perfect square. Okay, we're going to do another one of these. We're going to solve z to the power of 6 equals 1. We're going to plot these roots on an Argand diagram. So I'm going to do it the slightly longer method, even if there is a quicker method, just because I'm interested to keep using that method we've done so far. So z to the power of 6 is just going to be e to the 0i, putting it in exponential form. So z is going to be e to the 0i to the 6th. So z1 is just going to be, well, that's just 1 to the power of a 6th, which is just 1. Now for this case, we would usually be adding on plus or minus 2 pi over n. So in this case, that's going to be 2 pi over 6, which is adding and subtracting pi over 3. So let's get going. We're going to have e to the pi over 3i. If I add on another pi over 3, I'm going to get e to the 2 pi over 3i. If I add on another, I've written the same z here. Should have said z3, and this one is z4. If I add on another pi over 3, I'm going to get, this is pretty obvious, I'm just going to get e to the 3 pi over 3, which is just e to the pi I. And if I do z to the 5, I would get e to the 4 pi over 3. Now 4 pi over 3 is outside of the range, so I will subtract 2, which is e to the minus 2 pi over 3i. And z to the 6, well, I can add on another pi over 3 to this, and I get minus pi over 3. You'll notice that e to the pi I, we actually know that that one is minus 1 as well. So again, I'm going to put these onto an Argand diagram. And so the first one I have is at 1, as before. There's Z1. And I also know that Z4 is at minus 1. Z2 is pi over 3 of the way around, so it's going to be over here. And Z3 is 2 pi over 3 of the way around, so it's over here. Z5 is at minus 2 pi over 3, so it's going to be over here. And Z6 is going to be over here, which is at minus pi over 3. And we know that this angle between all of them is pi over 3, because each time we were adding on pi over 3, so the gap between them all must be pi over 3. Now if these angles are all equal at the centre, when I connect these all together, even though it doesn't look very neat the way that I've drawn it, I'm hoping you can see that we have drawn a regular hexagon. So, how would the solutions to z to the n equals 1 look on an Argand diagram? Well, let's see what we've got in common with these three shapes we've drawn so far. We had an equilateral, we had a tilted square, and we had a hexagon, a regular hexagon. So I think that we would have, for z to the n equals 1, we would have an n-sided polygon. And I think there's some more things we can say. Looks like they've all had the center at the origin. So there is going to be an n-sided polygon. The center will be at the origin. And we want to try and take into account the fact that the square and the triangle look a bit tilty. Hopefully you've spotted that Z1 is always at 1. So I think the third thing we can say here is that one of the vertices will be at 1 on the Argand diagram. So this is what happens if you take the roots of unity. No matter how many roots there are, they will always form a polygon, a regular polygon. The center will always be at the origin, and one of the vertices will be at 1. Okay. So we're going to try and explore a bit more about this because this is really interesting. So I've now plotted a much nicer looking one of my 6 roots of unity. So I've got 1, e to the pi over 3i, 2 pi over 3i, e to the I pi, the minus pi over 3, and the minus 2 pi over 3i. A couple of things that we notice here is that 1 will always be a root. I guess the reason that makes sense is because if you're saying you've got a number raised to any power is 1, well, obviously z could be equal to 1 because 1 to the power of anything is always equal to 1. The other thing, though, I'm going to start doing is I'm going to say, suppose that the next root around the polygon is called omega. So this one is 1. I'm going to call this one here omega. And then I'm going to try and think about how I get to the next one. So this angle that I've got over here is pi over 3. And then to get to this next one, we are moving around the circle another pi over 3. Well, think about what happens with complex numbers. If I want to take this one that I have here, this red dot, and I want to move it around the circle to get to the next one, if I multiply this complex number by the same complex number, in other words, if I do omega squared, I'm going to add for the arguments. The argument will be pi over 3 times 2. In other words, it'll be pi over 3 adding on another pi over 3. So this is the first one I've got. Omega has an argument of pi over 3. To get to the next one, I want to increase it by pi over 3 again, which means that this one is going to be omega squared. Now, do I need to worry about the fact of the modulus? Well, I don't need to worry about the fact of the modulus. Because it's a regular polygon, I know that the length of this line from here to here is 1. So even though I'm squaring it, 1 squared is going to just be 1. So the modulus will always remain as 1. So each time, I'm going to write this down, each time we multiply by omega, this is how you say that one, it's called omega, we move 2 pi over n around the polygon. So in this case, you would move 2 pi over 6, which is pi over 3, because we're doing it with to the power of 6. So we have 1 omega, omega squared, omega cubed, omega to the power of 4, omega to the power of 5, and then the last one that we have is omega to the power of 6. Now, this is interesting for several reasons. One of the things is going to be that we can have a look at what the sum of all of these complex numbers are. I'm just going to draw in these extra lines so that it looks familiar with what we did on the previous page. So these complex numbers are kind of like vectors that take us to all of these different places. And I'm going to try and investigate what happens when I add all of these complex numbers together. What happens if I did 1 plus omega squared plus omega cubed plus omega to the power of 4 plus omega to the power of 5? Well, if I think about this geometrically for a second, if I do this as vectors, I'm going to do a quick sketch where I'm going to draw this one for 1, this vector for omega, this one for omega squared, etc. So I would have, here's the origin, I would add on 1, then I would add on omega, then I would add on omega squared, then omega cubed, then omega to the power of 4, then omega to the power of 5. And I get back to where I started when I added all of these vectors together. Now, if I get back to where I started, that would imply that I haven't moved at all. That would imply that the sum of all of these things is equal to 0. So this is kind of like a geometric proof. But I guess instead, I could think about proving this using geometric series instead. So this was a sort of a vector representation. But instead, what I'm going to do is the sum of a geometric series. Because I have 1 plus omega squared plus omega cubed plus omega to the power of 4 plus omega to the power of 5. And I want to find out what this is equal to. Well, we know I need to find out what A is. A is 1. The common ratio here is omega. And the number of terms is 6. So the sum of these 6 terms, the formula is A r to the n minus 1 over r minus 1. A is 1. R to the n is omega to the 6 minus 1. And we have r minus 1, which is omega 1 minus 1. Now, if you notice at the top here, I said that 1 is equal to omega 6, which means that, coming back to this calculation, if omega 6 is 1, you get 1 minus 1 over omega minus 1, which is 0. And this is true for any n-sided polygon. We could say that the roots of unity sum to 0, as I've got written down here. This is true for any polygon. It isn't just true for the one that I've done with 6. It would be true for ones that I've done with n. So if I was to say that with the sum of n, it would have just been omega to the power of n minus 1 over omega minus 1. But because omega to the power of n is equal to 1, you get 1 minus 1 over 1 minus omega minus 1, which is just 0. So this is something that we really need to use in some of the toughest questions. And the thing that I need you to know is that the roots of unity, it has to be unity, they all sum to 0. And we're going to try and use that in a problem that we've got here, okay? So let's try this question, because this one is a little bit trickier than some of the other ones. Well, in some ways, maybe it's not that much harder. So we're going to solve z to the power of 5 equals 1. So I'm going to first of all go about coming up with all of these solutions. Now, obviously, the first one is just going to be 1. And the second one, we're going to be normally adding and subtracting 2 pi over n. So we're going to be adding and subtracting 2 pi over 5. So my next one is going to be e to the 2 pi over 5i. Then I'm going to have e to the 4 pi over 5i. Then I'm going to have, so I'm going to do 4/5 plus 2/5. And that goes outside the range, so I've got 6/5 here. Let's get it back inside the range, so I'm going to have to the minus 4 pi over 5. And my last root is going to be this one again, plus 2/5 pi. So it's minus 2/5 pi. E to the minus 2/5 pi I. And you'll notice that these are all going to be evenly distributed. So this is a gap of 2/5, this is a gap of 2/5, this is a gap of 2/5 from here to here, and this is a gap of 2/5 to here. So if we were to plot them, we would actually get a pentagon. Now pentagons are way harder to draw, so I'm not sure I'm going to do a very good job of this. So we should get Z1, Z2, Z3, Z4, and Z5. It is a pentagon with center at the origin and Z1 at 1, just as we predicted it would be. Now we know something about all of these roots. I know that the sum of these roots, I could write it that the sum of Zi from I equals 1 to 5, because they are all roots of unity, I know it's going to add to 0. So that means that Z1 plus Z2 plus Z3 plus Z4 plus Z5 is equal to 0. That's a fact I know because of this that I've got written here. So Z1 is 1. Z2, now I'm going to start writing these in their modulus argument form because the question wants something to do with the modulus argument form. So that's going to be cos of 2 pi over 5 plus I of sine of 2 pi over 5. Now Z3 is going to be cos of 4 pi over 5 plus I of sine 4 pi over 5. Z4 is going to be cos of minus 4 pi over 5 plus I sine of minus 4 pi over 5. And Z5 is going to be cos of minus 2 pi over 5 plus I sine of minus 2 pi over 5. And that is equal to 0. Now there's some things that we should know from earlier on, which is going to save us a bit of time. I know that the sine of minus 2 pi over 5 is the same as the negative sine of 2 pi over 5. So I'm wondering if there's any things here that might cancel out. Well, here we go. This, if I took the negative that's inside here, I can pull it out to the front for sine. So this is going to cancel with this. And this is going to cancel with this one that I've got here. Okay, so let's see what other things we can do. We should also know that the cos of minus 2 pi over 5 is just equal to the cos of 2 pi over 5. So that means that this thing is actually the same as this thing, and this thing here is the same as this one as well. So that means I've got 1 plus 2 cos 2 pi over 5 plus 2 cos of 4 pi over 5 is equal to 0. So 2 cos 2 pi over 5 plus 2 cos 4 pi over 5 is equal to minus 1. And when I halve that, I get cos of 2 pi over 5 plus cos of 4 pi over 5 is equal to minus a half, which is the thing that they wanted us to show. So these facts, we've been using them an awful lot. If you don't know them, you need to make sure that you know and can use these things, as they do an awful lot of simplifying in this problem. They didn't tell us to use the fact that the roots of unity sum to 0, but the fact that we started with z to the power of 5 equals 1 means that we're going to have to use that. So this should be enough to help you answer exercise 1F. There are some tricky questions in there. If you get stuck, use Solution Bank to give you some hints. And I would also advise using exponential form for as much of this question as possible. And I would also advise using this really neat shortcut of just adding on 2 pi over n rather than trying to do it in the way that they do in some of their examples. Okay, good luck with that.